In this lesson, we're gonna be solving this problem. Here, the sketch is written here. It's under hydraulic system, so it's a flow of water from this tank, upper tank, to the tank on the bottom. This tank, the upper tank here, we'll say it's tank number 1. Then this, the bottom one, say tank number 2. The water, it flows through this red nozzle here. It goes down here to drop on this point on tank number 2, which is a receiver. It receives water. It receives the liquid from the tank number 1, of which is the supplier one. So here we've got the horizontal distance up here, just up below the where the water drop from the tank number 1, drop on tank number 2. So that's horizontal distance. It is 600 millimeters. So the vertical distance from the water level of the tank number 2, it is 75 millimeters. Here we're given the data here. We have the diameter, which is a theoretical diameter, this 0.02 meters. Then we have got the actual delivery here, which is 0.95 times 10 to exponent -3 cubic meters per second. And here we are required to find the coefficients of delivery. It is here, coefficients of delivery. We are required to find this, coefficients of velocity. This we are required to find this, coefficients of contraction. This one, we've got some formula here to calculate every of these coefficients. Formula to calculate the coefficients of delivery, it is, we say CD, C to a subscript D is equal to actually delivery, which is Q to a subscript A, then divide by M theoretically delivery, which is Q to a subscript T. To calculate, that's the formula to calculate the coefficients of delivery here. So if you are looking at this formula to calculate the coefficients of delivery, here we've got the actually delivery here. Here it is the actually delivery. Can put it here, this actually delivery, but we don't have this part. We have to find it. So to find the theoretical delivery, we have to use the continuity equation. Let's say it is a theoretically delivery is equal to, you have to put there a theoretical area, and also you have to times with a theoretical velocity, like this. Theoretical velocity, a theoretical area. Here you can find the theoretical area here, this theoretical area. You can find it from this diameter, the theoretical diameter, this one. Let us find it. A theoretical area is equal to a pi, then a theoretical diameter squared divided by 4. Then to find the theoretical velocity, we use this formula, V to a subscript T is equal to a square root, inside is 2 times a gravity times a pressure head. So to substitute on this, the square root 2 times 9.81 times the pressure head. The pressure head, this H, it is this one, this H here, the pressure head. You put it, it is 1.25, give you 4.95 meters per second. That is a theoretical velocity. Now you have a theoretical area, you have a theoretical velocity. These two, when you times these two, it's gonna give you this theoretical delivery. Let us write it, this part. It is a theoretical delivery is equal to a theoretical area times a theoretical velocity. Then we substitute our theoretical area. It is here. We put it, then we times with this theoretical velocity. We found it now. Here it is. We put this 4.95. Then when you put this on the calculator, gonna give 1.49 times 10 to exponent negative 3 cubic meters per second. Now we've got the theoretical delivery. We are given the actual delivery. We can find now the coefficient of delivery. So the coefficient of delivery is equal to the actual delivery. Here it is. Then divide by the theoretical delivery, of which it is this one. This one we found it just now. We put it here. When you calculate this, it gives you the coefficient of delivery to be 0.637. That's the coefficient of delivery that you are looking for. This one. Now you have to find them. You have to find the coefficient of velocity. This one here. To find the coefficient of velocity, you have to introduce the formula to find coefficient of velocity. It is c to a subscript v is equal to actual velocity divide a theoretical velocity. It's like this. We do have a theoretical velocity. This one, it is here, but we don't have the actual velocity here. This one, we don't have. We have to find it. So let us find it. We use this formula. Actual velocity is equal to a square root, that is g times x squared divided by 2y. That's the formula to find the actual velocity. So when you substitute here, it's a 9.81 times the horizontal distance. That distance they are looking for, this one. It is x is equal to 600 millimeters. Then you convert it to meters. It is 0.6 meters. Here it is. You take this to put it there. Instead of x, it is 0.6 squared. Divide 2 that y is this y. You put it into meters. It is 0.075 meters. You put it 0.075. Then the answer here, it's gonna be 4.85 meters per second. That's the actual velocity that we've been looking for here. Then we substitute. It is 4.85 divided by a theoretical velocity. This one, it is here. This one, a 4.9. We put that 4.95. It gives you 0.98. Give you that number 0.98. That's the coefficient of velocity. This one's a coefficient of velocity, this thing that you are looking for. Now you have this and you have this. You have to find now this coefficient of contraction. This one. To find the coefficient of a contraction, it is simple, because a coefficient of contraction, it is c to a subscript c is equal to, it is a coefficient of delivery divide the coefficient of velocity. You have the coefficient of delivery, you have the coefficient of velocity. Then you substitute cd, you've got it, it is here. You put it 0.637 divided by the coefficient of velocity, it is here, it is 0.98. When you put this on the calculator, gonna give you 0.653. That's the coefficient of contraction, this one. Now you find all your answers here. You find CD, you find CV, you find C to the subscript C, which is the coefficient of contraction. That's what they were looking for. You find it all. So the formula to calculate this, I'll write it clear here. It was CD to the subscript D is equal to, it was actually delivery and theoretically delivery. Then the formula to calculate the coefficients of velocity, it was actually velocity and the theoretically velocity on the bottom. Formula to calculate the coefficient of contraction, it is equal to a coefficient of delivery divide the coefficient of velocity. That was the formula here to calculate these coefficients that they were looking for. So we all have found, we found this, we found this, we found this, we are done. When you're looking at this sketch here, when you look here on this sketch, here the pressure, it's 1 atm, and also here immediately after the nozzle here, the pressure is also 1 atm. So the pressure here and here are the same. Then here the velocity is 0. Here that velocity immediately after the nozzle is not 0. It's not 0. This pressure 1 atm here, it makes simple to find them, to find this theoretical velocity. When you take the Bernoulli's equation here, it's like this. So this, both of this, it's gonna give you a pressure head. It's height 1 minus height 2. This, because this is 1 atm and the pressure 2 is 1 atm, so this gonna cancel, and the velocity here on top is equal to 0. That means this side is cancelled. Then when you take height 1 minus height 2 is equal to, we left with this part, a velocity divide 2 times g, like this. Then this is equal to a pressure head. When you rearrange this, it's gonna give you, so I wanted to illustrate that part a little bit so you understand what is going on about this structure, because here they are talking about this. Here it's a height 1, this is a height 2. So this pressure head, it's simple, a height is equal to height 1 minus height 2. It's simple because these pressure are the same. This is pressure 1, here it's pressure 2, both are 1 atm. So here the velocity 1 is 0. Here the velocity 2 is not equal to 0. That is the theoretical velocity that we are looking for here. Theoretical velocity here it is. So that's why here it didn't cancel to be 0, like here the velocity 1 that is on top of a height level of the liquid here in tank number 1.